Okay, so there we go. We got the recorder going. All right, so we have a test. Let's talk about the test. Which way would you guys like to take the test? Here's those two different stories here. We don't have a ton of dates left. I don't know exactly how many we have, but I know next week we only meet twice. And the week after that, we probably only meet, I think the next week is a college week, so I think we meet 3 times. Okay, that gets us to the 4th of April. I'm sorry, the 4th of May. So that means we've met 5 times yet. And then I think you guys' finals are like something like the 10th and the 11th of May or something. Could that be right?
They have it earlier because we graduate IB Tech on the 11th.
Okay, so then maybe even be early. So we probably only have like 5 days left.
So let's do a take-home.
That's where I was going with this. Here's the deal. If we do a take-home test, we have the advantage and the disadvantage of we cover a little bit more material, right? We'll have 1 more day to work with. On the one hand, you get the advantage of you get to take the take-home test at home on your own time, no pressure, you look things up, whatever the case may be. And that probably will mean you'll have a better grade on that thing. On the other hand, it does mean we have 1 more day, we're going to get farther material. Okay, does that make sense? On the other hand, I think because we are about a day behind my original plan, it probably isn't a bad idea that we have. I mean, I think we'll get through about 4 sections of the next chapter. Yeah?
Are you writing the final for this class?
Yes.
Then could we possibly just cover more material and then have the final over both sections?
Ooh! You are saying that you think you'd rather take a bigger test over and not take a test right now? Is that what you're saying?
Yeah.
Interesting choice.
But the final will be
Oh yeah.
Okay. So not good with either option.
Joe has made a bold choice here. Joe has proposed we don't do a test right now and just move forward and then make the final over more material. Matt, tell me the pros and cons of that plan.
Pros, we don't have to have a review date today.
Yeah.
Cons, we probably cover less questions on the test concerning each section, so it'd be harder to make up in a certain area if we didn't study in that area because we can only spend so much on the final. Spend so much time on the final.
And it could take a long time.
Here's what I'm wondering. I don't know that in this grading period we've had any tests. Have we had any tests since the last grade? Somebody's got RDS handy. Did we take a test, or was our test on the, have we had any, I don't know that we can have a grading period with no tests. Where I'm going.
Yes and no.
Because there's a formula. What?
Yes and no.
That is true.
We had one 3rd grading period, however, it was so close to the end, it wasn't put on until this grading period. So
Okay, but it is recorded in this grading
Yeah.
period?
yeah.
Yeah,
Okay,
but technically-
because here's the deal. I don't want there to be like a divide by 0 error in RDS. You know what I'm saying? Where like, because like I believe there's a formula that's going to be like, it's like 1/3 homework plus 1/3 tests plus 1/3 the final or something like that. Okay? And frankly, everybody's doing fine. It isn't like we're throwing somebody's letter grade into chaos if there's, you know what I'm saying? I mean, we're doing fine on these things. So in that regard, I'm not worried about it. And as long as that 1/3 that's test wasn't 0, and don't get me wrong, rules are going to be broken. I'm sure with somebody call over to IB Tech or to RDS support, they can fix that. But as long as they have a grade, I don't know that I think I care. Okay? How does everybody else feel about the idea of not a test right now? I'm okay with it.
I'm okay with it. It's just the idea of how it will be longer and it'll take more
Well,
time.
here's why I am thinking that it's not such a bad thing. I feel like this chapter was long and disorganized.
Yes.
I mean, what, it was 10, 11 sections long, something like that? And it was sort of all assorted topics with derivatives, like mean value theorem, and fundamental, no, it wasn't fundamental theorem, Raleigh's theorem, and Newton's method, all of which are neat, but all of which are very different. When I was thinking about this test, what occurred to me was, even if I only asked one problem from each of those sections, it would already be a big test. Okay? And I'm not really sure I feel like in a classroom testing, let's say we thought on Tuesday we're taking a test in here, I'm not sure you under pressure right now being able to regurgitate, let's just pull something at random here, limits of infinity and asymptotes, impresses me or doesn't impress me, right? I mean, in some ways, it's kind of a disorganized bunch of stuff. I think possibly you guys doing the homework is enough proof to me that you got through each of those topics. I'm not sure the fact that you crammed it and can regurgitate it on a test impresses me anyway. So I'm inclined to say we move forward per Joe's suggestion and we pick and choose some things from chapter 4 that will be on the final. Some of the more key things, like it's hard to have a calc final without mean value or whatever that, I don't know how you would call it, mean value theorem or whatever. It's pretty hard to do this without like maxima and minima. Yeah. Okay? Whereas applications of applied optimization problems, the fact that you did the problems probably is proof enough. I'm not sure we need to test on that. So I'm going to move forward. Now, is there anybody clenching their jaw and saying, God damn it, Joe, I'm sorry, I shouldn't be looking at Freddie. Why did you say that? Is anybody here?
Jared.
Yeah.
Jared. I'm sorry, Joe, not Jared. Joe. God damn it, Jared just comes all the time. It's the problem. No. Joe. Eric, are you okay with this plan? Okay.
Jared won't be, but he doesn't have to say because
Jared-
Jared's here.
Jared's not going to do
Jared's
good
not-
either way.
Jared's not going to do good anyway. Jared's watching.
He literally hasn't been in the
It's
class.
going to be fine. The point, okay, so here's the deal. I actually am a little bit stoked about the possibility of moving forward. But I'm not all that prepared yet, but hold on. Let's talk about antiderivatives instead, because Joe has had some intriguing questions about some of them. Let's spend a little bit of time fixing a few things with that, and then starting to talk about section 5.1. Okay? So Joe came across some problems that he he was having trouble finding how to solve.
What section is it?
We're looking still at the last section of 4.11 or 4.9 or whatever this is.
Is that over
4.10.
12?
What? No, what we thought we did, that was 4.8. This is 4.10. Right? Just the assignments from the other day, right? So, Joe, name a problem you're having trouble with getting to finish up here.
483.
483. I'm scrolling over here to 483. All right. Joe had trouble with, oh my gosh. Let me think about this one here. F of x equals the sine squared of x times the cosine of x. Is that the right one?
Yeah.
All right. Now, what it is asking there on those problems is to find the antiderivative for this function. So you're trying to find this big F such that F prime is equal to this thing. Okay. Joe had a great question about the whole business of why are we sometimes calling this the big F and sometimes we're doing this with that integral symbol. And the answer is it's very related to the fact that we had that F prime sometimes that we were using, and sometimes we were using d by dx as the symbol of the derivative. It is two different ways from the fact that calculus was invented twice. Remember, Leibniz did it and from someplace in Pomerania or Saxony or something, and a country that ain't around anymore, someplace in Northern Europe. And Newton did it independently in England while hiding from the Black Death. And it's just two different sets of notation. Okay? After we move forward with this, we're always going to be using the integral symbol. All right. I am going to suggest that I get a student. Okay. I was going to send somebody to the board to do this one, just because I'm not prepared. I don't have to have that. So I was thinking we were doing a review today, but I think this is a better plan. So if I look over here, hold on just a second. I'm pulling this 9-point page out here. There it is. All right. So Joe said this is a hard one, and he said, I just want to check on one more thing here. This is not an impossibly difficult problem. I'm trying to think of how we do this in the context of section 4.10. Who got this problem to work? I bet one or both of the twins got this problem to work. Did you get this one to work? Look how she points accusingly. J'accuse! Did you get number 483 to work?
1 second. Let me look at the
What function f of x is this going to be the derivative of it?
wouldn't that be, 1 second. Well, it'll be, okay, so that's the derivative derivative of something,
Uh-huh.
right? Okay, so the cosine would be sine, and then
Is that what you have to have?
that's something else.
Where are we at on this one? Hold on.
Sine is cos, right?
Yeah,
And
so
there
the
is
cosine would be sine.
Cos is negative sine.
Sine squared.
Because
is-
again, I mean, this is the kind of thing.
Sine squared is tangent, cosine is negative sine.
Here,
But
four.
because
Okay, so
multiplication is
this is
equation,
483,
it's
right?
all like that.
Yeah.
Am I wrong? It looks to me like it's 1/3 sine cubed. 1/3 sine cubed x plus the big C. Okay. How would we have known this? Now, Joe, clever lad that he is, use some kind of calculator or some app or some website? Is that what you were saying? How did you? Where you said your calculator or something was telling you the steps of how to do this?
Yeah,
What was it?
symbollab.com.
Symbollab.com. Okay. So, I agree. Symbollab.com. Something like that. I would have gone for Wolfram Alpha, but all such things would work. If you type you want the indefinite, if you go into Wolfram Alpha and you type in I want the indefinite integral of this, it will gladly give you this, but either not tell you how it did it, or it'll use fancy tricks that we have in later chapters. Okay? Or later in chapter 5 or whatever. Let's verify this. Let's leave this alone for a minute in terms of how to get the other way around. Let's say, hey, is the book right in the first place? So is the derivative of this thing? All right, so this is one, if we're asking f prime of x is equal to 1/3, just to make the notation a little more clear here, sine x cubed plus some c. And we want to know what its derivative is. The derivative of big F equals. This is a chain rule problem, right? It's like a power rule with a trig rule inside of it. So this is 1/3 times 3 times the inside raised to the square times the derivative of the inside plus the derivative of c, which is 0. 1/3 and 3 cancel out. Sine squared x cosine x. It checks out. Did you get this one to work? Did you get this one to work? 483.
I see.
You skipped that one. I agree. Here's the deal. I bet if we went through all the examples back there in section 4.10, there are some, the nature of this book is they probably are reproducing one of the examples or something like that. But here's the deal. I don't see immediately how you would have gotten this. Derivative of this times. Do we have a derivative? Let me look at that table real quick here. Hold on. Before I tell you that, let's not worry about this problem. Let me look one more time at something. That table of indefinite integrals that they've got there, do they have one that is...
Not one set up like this where you're multiplying two non-constants together. They've got one where you
Yeah.
multiply by a constant.
The trick of this one here that made this one work, there is in that kind of table, remember how I said that table that's in there that had all those examples of indefinite integrals becomes a bigger and bigger and fatter thing in a calc textbook where there's all these pages of integrals in the front of that book that some sad math major someplace derived. Okay? There is one out there that is something like g of x, some function of x to a power, let's call that power n, times the derivative of that power. I mean of that function. So like if your f of x could be written as, here's a little function raised to some power times the derivative of that function, then the integral is, then the integral of that will be, or the antiderivative if you want to write that way, it's going to be 1 over n plus 1 times that same function g to the n plus 1 power times the derivative of that g plus the big C, which is what we have over there. But we don't have that rule yet. So I'm not entirely sure how, because then this g could have been sine, so that would have been sine squared, and that's derivative of sine is cosine. That pattern would have worked. We don't have that rule yet. So I'm not entirely sure if that's a mistake or if there was something we should have done. When you went into symbollab.com, Joe, what did it tell you how to do this problem?
It said that there was some sort of substitution you had to do with u.
Ah, yeah, that's another way to do this. Yep.
You don't
U
put that
du.
little 5 point.
Yep. U could have been equal to sine of x, then du equals cosine x dx. So the integral of sine squared x times cosine x dx would be the integral of u squared du, because this is equal to du. And that would be 1/3 u cubed times du? No, it's 1/3 du. 1/3 u, yep, plus c. Yep, that's another way to do it. That's method of substitution. Hey, that's going to be, yep, 5.5 in our book. Yep, that's another way to solve that problem. I like both of them. Neither of them has crap to do with antiderivatives. So I vote we just don't care. Here's the deal. Did everybody make progress on section 410? The ones that seemed age appropriate, like, hey, we're just learning the beginnings of doing derivatives, like the power rule ones and the simple trig rule ones and so on. You got some of those to work? We're happy? Shall we move forward? Okay, let's move forward. Because we're going to be doing better things with that anyway. Okay, I am less nifty, prepared, like I've read, but not like prepared a lecture on, I know you're shocked to think I prepare for these things. But let me show you where we're going with it. Let's start talking about 5.1. We always learn about derivatives before we learn about integrals, which in some ways is weird. Both Leibniz and Newton discovered the other one first. Not the other person, the other one. Integrals first. But for various reasons it makes sense to learn derivatives before you learn integrals. Now, the nature of the problem that we're trying to solve when we are taking an integral is we have some graph here and we have some function. Whee! Here's a graph of some function. We already know all about derivatives. But here's another thing we can wonder about. Over this range, from x equals a to x equals b, what is this area underneath here? Now you might immediately say, who gives a damn? Why would we care? The truth is, this is everywhere. Let me give you an example. Let's say this graph, I'm going to use a meteorology example, because that's what I know, right? Let's say this is a graph of time versus solar heating. How much heat you're getting from the sun at each moment. So like maybe as the sun was getting higher in the sky, you got more and more sun, and then maybe a cloud went over between the sun and the ground, and so you got less sun for a while, and then you got more sun as the cloud passed away. The total area underneath here would be like the total amount of heating you got over that time. At any given moment, time, I'll just label it time t, you got this much, and at this time you got this much, but the total amount of heat, you add up all these little stripes that you got over that time, is the integral. So if we had some function f of x that was whatever this is, the integral of f of x dx from, I'm going to write out something here, from x equals a to x equals b. We don't usually write the x equals part, but it makes it a little bit sense. It helps you understand the notation. We'll quickly graduate from doing that. Notice how we've got these little clusters of symbols on here, though. Is this area. That is what this is. There's a right word for this. This is called the definite integral. The definite integral has these limits of integration on here, the beginning and the ending place. It's defined. That's the sense of the word definite here. Not as in like definitely yes. No, as in it's defined. This is where we're heading with this. The ability to find the area under a curve, between the curve and the x-axis, is in fact a fancy way of saying lots of things in physics, business, engineering, all kinds of problems. In order to do this, I need to first think about what I would do if I didn't have calculus.
If you didn't have calculus, it seems like you'd get an infinite number.
Yeah, well, there you go. You're heading in the right direction, actually, with that.
Because if you added up all the stripes, well, then you can keep on adding.
You just keep on making them smaller and smaller and smaller, right?
Right.
Yes.
So the integral sign, does A always have to be the smaller of the two numbers?
No. But in practice, for most story problems, that's the way it's going to be. In general, you're right. Let's say the left is going to be here, and the right is going to be here. Does that make sense? Like, this is this end, and that is that end. So, like, this would be from A to B. But it doesn't have to be. We can make problems that they don't, but that's going to be 99% of the time the way we're going to do it, okay? All right. If we were just making a stab at this. If we were just taking a stab at this and we said, you know what? I don't know how to find the area of this. But you know what I do know about the area? Rectangles. I could say, you know what? I could divide this thing up into a bunch of rectangles and add those rectangles up. Here. I'm doing it right now. I'll call them rectangle 1, 2, this pen sucks. I'll call it rectangle 1, 2, 3, 4, 5, 6, 7, 8. Some of those rectangles are not as big as the area, like from little a to this little right here. I mean, we're kind of losing this little piece right here. But some of the rectangles, like number 4 here, are a little bit extra. And I'm not going to prove it to you right now because it's brief calc, not real calc. That sounds terrible. That's so detrimental. This is brief calc, not calc 1. We don't need to prove it. But we can prove it that in general that's not going to be a terrible way to guess, right? If we wanted to have the areas of these rectangles here, we could figure out the areas of each of these 8 rectangles and add them up. What would the areas be? Well, first off, let's figure out how wide they are along the bottom here. This distance from B to A has been broken up into 8 pieces. So B to A has been broken up into 8 pieces. So each of them is this wide. May I make myself a happy teacher and call this something else? Rather than writing this out a bunch of times, let's call that delta x. This little distance right here is delta x. This is delta x. This little distance is delta x. Let's just make ourselves happy here. Hey, by the way, if you're thinking that little delta x and delta starts with the letter D, and we've seen dx's before, right? Right? I'm heading towards something. Each of these little rectangles then is delta x times some height here. And that height has something to do with the function. How about we call this place here like f of a. So this little triangle, rectangle right here is f of a times delta x. That would be his size. And this little guy right here would be at f of a plus delta x. And this little right here will be at f of a plus 2 delta x. And we have each of their sizes there. So rectangle 1, his size will be delta x times f of a. Rectangle 2, his area will be delta x times f of a plus delta x. Right, we're a plus delta x over, and we go over here. 3, delta x times f of a plus 2 delta x. We're looking for a pattern here. 4, delta x times f of a plus 3 delta x. All the way up to rectangle 8. And then we could add them up. And we've made pretty damn close. You can imagine Newton and Leibniz at the same, almost the same time, but a continent apart, both saying, how neat. I can solve problems about the acceleration of planets going around the sun by my new law of universal gravitation, so says Newton. I'm not, where like maybe this is the equation here might be the force that was pulling on or whatever. Hey, let's actually add those numbers up. Add all these bad boys up. Boy, that looks annoying. This plus this plus this plus this. I need a better way to write this, but this isn't your first day. You know about sigma, right? Sigma notation. A happy way to write adding a bunch of numbers up. Where you put down here a counter and where it's going to start, I'll call it I, where I will go from 1 to 8, because we're adding up 8 rectangles, their area here. And each of those rectangles has some area. Delta x times f of a plus I minus 1 times delta x. This right here is the area of rectangle I. When I is 1, when I is 2, when I is 8, you add them all up. Why did I choose 8? Yeah, why didn't I choose a bigger number? Because I just was writing with a big fat pen, right? Is this number going to be the same thing? Here, I'll put a question mark. Is that going to be the same thing as that actual area, the area of f of x dx from a to b? Is it going to be exactly the same? No, it's going to be an approximation, but it's going to be pretty darn good. But what would make it even better? More ends, right? Make more and more. Here, let's divide this same thing up into even more little rectangles. It can be shown, again, we're in brief calc, so we don't have to worry about that. But it can be proven that actually the more pieces you break this up, the smaller and smaller n gets. You get closer and closer to the actual value, excuse me here, of that integral. So instead of this being 8, how about we call this n? N pieces. That, remember there, that we better make sure we understand that delta x is b minus a over n. Right? Because the widths of them are getting smaller and smaller and smaller. And both Leibniz and Newton were bright lads who were then saying, wait a minute, what if I got it really, really small? Matt is also a bright lad, a brightly dozing lad. Matt is sound asleep. Matt. fond words about you at the moment. Matt is a brave, bright lad, and correctly said, what if I added up an infinite number of these guys? Right? I mean, it kind of seems like there should be, oh my God, are we using limits again? You sure are. It seems like there should be some limit here. Or like, as n got bigger and bigger and bigger, I'm adding up a bigger and bigger number of these things. And it should be getting better and better and better, in fact, at infinite. Hey, how wide are those rectangles then? How wide is each rectangle? B minus A divided by n. How wide are those rectangles? What? Small. As small can be. There's actually a mathematical term for that. Infinitesimal. Infinitesimal. They're as small as it gets. Right? They're getting really, really narrow. In fact, we have a better symbol for it. At that point, we switch over and call it dx. They're little bitty things. But we are integrating, adding up all these little pieces. Little rectangle, little rectangle, adding up an infinite number of little tiny rectangles. And again, we could actually prove that as the limit approaches infinity, this sum is this. In fact, that's what this is. The integral from a to b of f of x times dx is just another way to write that. Because remember, hey, wait a minute, what is sigma? What is that letter of the Greek alphabet? It's the same as the English letter S. Hey, what was this curly integral symbol? It's a weird way of writing the letter S. Okay? It meant summa or something like that to Leibniz or whichever one introduced that symbol. A Latin word that means add up. This is just another way of writing then. We've summed up all these little rectangles, each of which is this tall and this wide. That's what we're doing here. Now, your book spends a fair amount of ink, it's not ink, it's screen time, but whatever, of making sure you're happy with this business of sigmas, as like adding things up. But I didn't see anybody's forehead furrow in anxiety when I put a sigma up there. Were you guys okay with that guy? I mean, like if we had problems on the homework set that involved things, for example, like the sum as I goes from 1 to 5 of I squared, I feel like, because there are problems like that where they're just giving you exercises in using sigma. You understand that that would mean 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, right? You know how that sigma works, right? And like, for example, on this problem right here, I mean, that delta x is a constant, right? Whatever b and a are and whatever n is, they're constants in this problem. We could have pulled that constant out in front of here. Because, I mean, it was more obvious when I had it written all out here. Delta x times something plus delta x times something plus delta x times something. We just factored the delta x out. Okay, your book spends way too much time making sure we're all on the same page about those kind of rules. I feel like the crowd is happy with those rules. Okay. Let me just see here where they all go with this then. Okay, because I can't remember exactly. Okay. This diagram, let me thin it out a little bit and go back to kind of more where we were. So here was our function from A to B, and we divided it up into pieces. You might have noticed something here. I deliberately made it so that the height of each of these rectangles is where the left corner of the rectangle touched the function. This place right here, the left corner is what became the height. And this one, the left corner is what became the height. And and so on. That is called, what's the book use it there? That's called the left endpoint approximation. That's not the term I used for approximation. But we could have drawn it another face. I mean, those heights of those triangles could have been based on the right side. Like our first triangle could have been where it touches here, and our next triangle could have been where it touches here, and our next triangle could have been here. And we could have worked this all out, where it was, you know, the sum of each of these delta x times f of x plus delta plus I times delta x. It's a little bit easier to write that way, summation I equals 1 to n. All right, it would have been fine that way too. That's called a right end rule or a right end approximation because you're using the right side. Or you could use the middle, a midpoint approximation. And the book all has lovely diagrams illustrating all these things way better than I can draw. And it can be shown that it does not matter. The left end approximation to these integrals is not exactly the same thing as the integral. The right end approximation is not exactly the same thing as the integral. For that matter, the midpoint, where you get the middle of the box where it touches the function, is not the same. But they're all really close. And the bigger and bigger n gets, they all, in the limit, as n gets towards infinity, gets to be closer and closer to the actual integral. That is enough for today. Where we're heading with this, though, is to be able to actually compute the integrals as areas under these curves. So, for example, if our function was this, f of x is x squared. If you wanted to know the area from a equals 0 to b equals 5, we now know what this is going to be. It's going to be the integral from 0 to 5 of x squared dx. And even with just our crappy section 4.10 that was the antiderivative one, we now know how to do this antiderivative. It will be 1/3 x cubed. Well, it was 1/3 x cubed plus c. Now we're going to have to find out something we can do to this using that value a and b, which it's actually 0 and 5 in this problem. That's called the fundamental theorem of calculus. So we're a little bit away from that, but just to show you what it is, first you plug in the top number. So 1/3 times 5 cubed, which is 125, plus, then you plug in the bottom number, 1/3 times 0 cubed. That'll be 1/3 of 125 is 125 thirds, and that is the area under this curve. But that's the fundamental theorem of calculus. We're not quite there yet. But we are like just about ready to fling ourselves off the cliff and into the warm and loving embrace of the fundamental theorem of calculus. You didn't think I'd stick the landing on that metaphor, but I think I did. I think I did. All right, so I don't actually have a homework set picked out for this this chapter yet. And not this chapter, because I think that's part of preparing. So let me. Yeah, let's do these problems. Let's come up with a list of problems to do. Because like I said, I was thinking we were reviewing today. This is way better. So, we're on a new chapter. We get to start with small numbers again. Page 523. Let's do one. Well, okay, because you know I haven't done the problem yet. How about 1 through 7 odd? And let's also do okay. How about 13, 15, and 17? Let me give you some notation stuff here about 13, 15, and 17. So right now what they're saying is like, if you have some function, f of x equals x squared, they want you to compute L4 for the range 0, 1. What this big L here, this is not some standard notation, this is something your book made up. L means it's the left-hand rule, or the left-hand and left endpoint method. And 4 means how many, like what that should be n. So they're saying divide up the area from 0 to 1 into 4 left-handed pieces, or left endpoint pieces. So like this will be 0, 0.25, 0.5, 0.75. This first triangle here, f of 0 is 0. This one will be at f of 2.5 is 2.5 squared, that kind of thing, okay? And some of the problems have big R's, that means it's use the right-hand rule instead, okay? And that subscript is just how many they divided up into. If there's any of these problems, first off, there's not that many problems, we're only 7 problems, but if any of these problems are like outside of what we did today or something, obviously just let me know. This is not as prepared as it normally should be. Yay me! I like moving forward and not taking a test. All right, let me stop this here.
I've got some homework assignments.
Oh, okay, hold on.